This full coffee mug has a mass of 600 grams, or 50 times that of the 12-gram robot hiding behind it. This robot is able to move forward, turn, and raise and lower its belly at will. Here's the cool part though, when the micro-robot decides to, it can easily move objects more than 50 times its mass. This is accomplished using the magic of directional adhesives like ants and geckos use in nature. Here we look at how the robot is made. It has a controllable adhesive base with a large winch, tow cable and hook, along with a microprocessor and electronics. The winch is used to both pull the large loads and raise and lower the drive wheels here, controlling contact with adhesive on the ground. Now that we know what's going on, let's take a closer look at that video. We see here the adhesive raising and lowering from the surface freely without sticking. This is because the adhesive isn't sticky until it starts to pull and shear. Then when the robot wants to, it puts its belly on the ground and pulls in shear, thus sticking it to the surface. The controllable adhesive used allows these robots to dramatically outperform comparable friction-based robots. Here we show the same 12-gram robot repeatedly pulling over 4.2 kilograms, or 350 body weights. Note how it engages its adhesives, pulls for a cycle, releases the adhesives without sticking, drives forward, and repeats the cycle. Finally, we show the 12-gram robot moving 21 kilograms, or 1,800 body weights. This test shows the limit of the actuators, not the adhesives, which should be able to move almost twice that much. The same principles can be used for the solid-state actuators that would be necessary for further size reduction. Piezoelectric PZT bimorphs demonstrate the adhesive's impressive speed, but for reasons discussed in this paper, will be limited by the amount of work per cycle they can achieve. Shape memory alloy, on the other hand, can harness the full force of the adhesives with more than 100 times the work per cycle of piezoelectric bimorphs, allowing this 6-gram prototype to move 2.5 kilograms here.
A team of researchers at MIT and elsewhere have developed a tiny origami robot that can unfold itself from a swallowed capsule to complete specific tasks within the body.
The robot can remove foreign objects, it can patch wounds, or it can deliver medicine at designated locations.
This new ingestible robot builds on the team's previous work on mini origami robots. However, the design of its body is significantly different.
The challenge with designing an ingestible robot is finding biocompatible materials that are easy to be controlled and amenable to the types of operations that are needed from the robot.
To address this challenge, the researchers tested about a dozen different possibilities for the structural material before settling on a type of dried pig intestine used in sausage casings. To demonstrate how the robot works, the researchers folded the structure into a capsule made of ice. The ice capsule travels down the esophagus into the stomach, where the ice melts away and the robot unfolds to its functional form. At this point, the robot can be controlled by an external magnetic field to do work, such as the removal of a foreign object from the body. For example, every year, 3,500 swallowed button batteries are reported in the US alone. The tiny batteries are digested normally, but if they come into prolonged contact with the tissue of the esophagus or the stomach, the batteries can burn the tissue and become embedded. Now, using the team's new robot, the battery could be removed without surgery.
Once inside the stomach, the robot could be directed to attach to the battery. It could lift the battery from the stomach coating and then eliminate it through the digestive system. Next, we would like to do in vivo experiments. We would also like to add sensors to the robot and redesign the robot so that it's able to control itself without the need of an external magnetic field.